Good afternoon, everyone. Let us start.
Good afternoon, sir.
Remember, we have been learning Chapter 3, Interior of the Art. Last time we discussed about different sources of information about the art interior. We discussed about direct sources of information, and we also started discussion about the indirect sources of information. Now let me present. So today we shall discuss seismic activity as one of the most important sources of information about the art interior. Last time we already discussed meaning of earthquakes, why does the art sack, that is, how does earthquake occur, and now let us discuss about earthquake waves. So before we start, you have to know that earthquake waves are recorded by an instrument called seismograph, and see this instrument from the that record the various types of earthquake waves. By analyzing these earthquake waves, we can infer what is there in the art interior, what is the nature of the art interior. Now let us start. So before we start about analyzing the art interior, we have to learn the different types of earthquake waves. What are the different types of earthquake waves? So earthquake waves are basically of two types: body waves and surface waves. Then what are body waves? See here, body waves are generated due to release energy at the focus and move in all directions, traveling through the body of the art. Let me repeat, body waves are generated due to the release of energy at the focus. At the focus means the point of origin of the earthquake, and from that focus waves move in all directions, traveling through the body of the art, traveling through the material, okay, body of the art, and hence the name body wave is given. See here, here in this area, so this is the place where energy is released, and this is called focus, and from the focus different waves are propagated, okay, through the body of the art, and hence the name of body waves are given. And the body waves interact with the surface rocks and generate new set of waves called surface wave. See here, the body waves, say for example here this is the art, and here an earthquake has occurred, and let us suppose this is the point of origin earthquake, and from here body waves are propagated. Body waves are moved in all directions, and when these body waves reach the surface of the earth, it is interacted with the surface rock, and a new wave is generated, and this new wave is known as surface wave. Okay, so from this point of origin of the earthquake, body waves are propagated, and when the body waves reach the surface of the earth, it is interacted with the surface rocks and materials, and another type of wave is created, and that is known as surface wave. So these are the two main types of these earthquake waves. Remember, we have two main types of earthquake waves. The first one is body waves. Body waves move through the body of the earth interior, and when the body waves interact with the surface rocks, these generate a new shadow waves known as surface waves. And these surface waves move along the surface, okay, not through the body of the earth interior. Surface waves move along the surface, and hence the name surface wave is given. And here see some important this nature of the earth. These earthquake waves are given here. The velocity of waves changes as they travel through material with different densities. That means the denser the material, the higher is the velocity. Okay, the nature of this earthquake wave is such that the velocity, the speed of the wave changes as they travel through materials with different densities. If earthquake waves travel through the denser material, then there will be higher velocity, and if it passes through the material having less density, then the velocity is decreased. Okay, and their direction also changes as they reflect or refract when coming across the material with different densities. So when earthquake waves move, okay, and their direction also may be changed depending on the density of the material. See, reflection, you know, reflection. See, this is the surface. Just let me give you this about reflection. Okay, this is here. Then this is what we call reflection. Okay, just for explanation, this is called reflection, and this is called refraction. Okay, just for explanation, see, earthquake waves change their direction. See, they may be reflected or they may be refracted, means bended when they cross the material with different densities. So this nature of the earthquake wave is very important to understand about the earth interior. Okay, let us proceed. See here, this figure describes these typical earthquake waves. And so remember, to the seismograph, P waves arrive first. Okay, P wave is the fastest wave, and it arrives at the seismograph first of all, and then after P wave, then S wave arrives, then after the S wave, surface wave. Okay, surface wave arrives. And here see, amplitude means half of the wave height. Okay, now let us discuss about these different types of these arc webs, the nature of these P webs, S webs, and surface webs. See here, there are two types of body webs. Okay, there are two types of body webs. They are called P webs and S webs. Okay, P webs and S webs are the two types of body webs. And as I told you, P webs move faster. Okay, P webs move faster and are the first to arrive at the surface, are the first to arrive at the seismograph. And these webs are also known as primary webs. And primary webs or the P webs are similar to sound webs. And they travel, okay, they can travel through gaseous, liquid, and solid material. Remember, P webs travel through gaseous, liquid, and solid material. Next, we have this S web. S web arrive at the surface with some time lag. That means after the P web, then S web will be arrived. Okay, and these are also known as secondary webs. And an important fact about S web is that S web can travel only through solid material. Remember, S webs can travel only through solid materials. And this characteristic of S web is quite important to understand, to learn about the nature of the Earth interior. Now let us see. Okay, see here. Let us say this is our Earth. And here, let us suppose an earthquake has occurred. Let us say this is focus. And from the focus, let us say different types of earthquake waves are propagated. Let us say this is primary wave. Okay, this is primary waves. Let us say this is a P wave or primary wave. And here this is another wave, okay, that is S wave, and S wave after traveling some distance it has stopped here. Okay, so this one is what? This one is S wave. This one is S wave. Now tell me, what is the nature of the Earth material, Earth interior here at this point? What is the nature of the Earth material of the Earth interior here at this point? Remember, here this S wave has stopped traveling at this particular point. At the same time, I tell you this P wave, okay, which can travel gases, liquid, and a solid state also reduce their speed. P wave has reduced its speed. At the same time, S wave, which can travel only through the solid state, has stopped here at this particular point. Then what is the nature of the Earth interior here? Tell me. What is the nature of the Earth interior here at this particular point? Anybody? Yes. What is the nature of the, whether this section of the of the earth interior is in solid state, liquid state, or gaseous state? Tell me.
Liquid or gas?
Yes, right. Because the S wave, which can travel only solid state, has stopped here. That means from this particular point onwards, the state of the nature, the state of the material, maybe in this liquid, or maybe in gaseous form. Yes. So in this way, by analyzing the nature of the archive webs, geologists can understand, can analyze the nature of the this earth interior. Okay. Any question from your side? Any question? See, it is also mentioned here. It has helped, the nature of the S web has helped scientists to understand the structure of the interior of the earth. And one more point you have to learn, and we have also read earlier, that reflection causes webs to rebound. Means this one. Okay, rebound means this one. Okay, this is called rebound. And this move, whereas refraction moves webs to move in different directions, and the variations in the direction of webs are inferred with the help of their record on seismograph that I have told you earlier. This, by analyzing the archive webs recorded on the seismograph, we can understand the nature of the earth interior. And in addition to these P webs and the S web, we have the last type of wave, that is the surface webs. And the surface webs are the last to report on the seismograph. It must be read as seismograph. Surface webs are the last to report on the seismograph, and these webs are more destructive. Actually, this is the web which cause the sacking and traveling of the earth surface. And this is the most destructive web. Surface webs are the most destructive web, and they cause displacement of the rocks, then collapse of structures, means collapse of buildings, and landslide. So many these destruction may be occurred due to this sacking of the earth caused by the surface web. So these are the three types of webs. Actually, these we have two types of body web, P webs and S web, and this surface web is another type of web, and it is not mentioned in the book, but surface webs are again divided into many subtypes. We have these relay webs, then lub webs, and the surface webs are also known as L webs. Surface webs are also known as these L webs. L webs. L webs. So let us continue. Propagation of earthquake webs. It means that how do earthquake webs move? How do earthquake webs move? That is propagation of earthquake webs. Now let us read. Different types of earthquake webs travel in different manners. As they move or propagate, they cause vibration of the body of the rocks through which they pass. P webs vibrate parallel to the direction of webs. P webs vibrate parallel to the direction of webs, This exerts pressure on the material in the direction of propagation, and as a result it creates density differences in the material, leading to stretching and squeezing of the material. Okay, so let me show you one diagram. Okay, so this is how P webs move. So this is the direction of propagation. See the arrow. Okay, this arrow tells the direction of movement, the direction of propagation of P webs. And here P webs cause this squeezing, okay, and stretching. See here in this place, this compression is here. Okay, here you'll find compression, then dilation, then compression, dilation. That means squeezing, then stretching, squeezing, stretching. So in this way these P webs move just like spring. Okay, so it is mentioned here. These P webs vibrate parallel to the directional webs, and this exerts pressure on the material in the direction of propagation, and as a result P webs create density differences in the material, leading to stretching and squeezing of the material. Okay, stretching and squeezing of the material. Just here squeezing, then after that stretching, squeezing. Okay, so next we have this S web. The direction of vibration of S web is perpendicular to the web direction in the vertical plane. The direction of vibrations of S web is perpendicular to the web direction in the vertical plane. So here in this case, okay, see, let us say this is the direction of movement. Okay, this is the direction of movement of the web. In case of this S web, it is perpendicular in this way. So this is about the S web, and here the direction of movement is perpendicular. Okay, here this is perpendicular, and here it is perpendicular. And let me show you another this diagram. This is about S web. How do S web propagate, move? See this arrow, the red arrow shows the direction of movement of the S web, and see here the webs are moving. Okay, this in this way it creates this crash and throw perpendicular to the direction of the movement as given here. The direction of vibrations of S web is perpendicular to the web direction in the vertical plane, just as I showed you earlier. See, in this way, this is the direction of propagation, and here these S webs are moving like this, up and down. So okay, in this way, perpendicular to the to the direct web direction. Okay, S web, the vibration of S web is perpendicular to the web direction in the vertical plane. Just see this diagram very carefully. Here, ups and down, perpendicular, then again perpendicular. Okay, and hence S web create throws and cracks in the material through which they pass. Okay, here this is what? This is known as crash, and this is known as throw. Okay, since S webs are moving perpendicular to the direction of the webs, So it creates this crash and throw in this way. Okay, that is what mentioned in the book. And see, I will show you one more this animated, okay, GIF is given here. Do you see here in this animation this P wave, okay, see here, P wave is followed by S wave. In the see here here is squeezing and stretching, and it is followed by this crash and throw. Okay, that means this P wave is followed by S wave. Okay, P wave is followed by S wave. So this is how these P waves and S wave propagate. And the last one, the last type of wave, surface waves. Okay, surface waves are considered to be the most damaging waves, as I told you. So surface wave, okay, causes this shaking and trembling of the earth surface, and hence it damages, it destroys the structures. And some diagrams of this surface wave. So this is a type of surface wave. Okay, so this is a Rayleigh wave. See here at the surface you will find this type of movement. Okay, this is known as Rayleigh. And then this is another type of surface wave. Here it is moving like this, and this is known as Love wave. Okay, LOVE, Love wave. This is Love wave, and this is Rayleigh wave. So both are the surface waves only, and it causes destruction of the earth's surface. Up to here, any question? Do you have any confusion about the propagation of the earthquake waves? Do you have any question regarding propagation of earthquake waves?
No, sir.
Okay, so let us proceed. This emergence of shadow zone. So what are shadow zones? Let us see. Here earthquake waves. Okay, earthquake waves get recorded in seismographs located at far off locations. However, there exist some specific areas where the waves are not reported, and such a zone is called shadow zone. Okay, so there are some areas on the earth's surface where earthquake waves are not recorded, and those zones are known as shadow zones. Okay, see here, you will find here in this case. So here in this section, these no earthquake waves are recorded, no P waves are recorded here, and here in this case also no P waves are recorded here. So this region where no P waves are recorded is known as shadow zone or P wave. Okay, and in the other case, see here in this section, in this region, no earthquake waves are recorded, no S waves are recorded, and hence this zone is known as shadow zone of S wave. Okay, so remember, shadow zones are the places where earthquake waves are not recorded. So let us read this paragraph. So when we observe this figure number 3.2, A and B, okay, it was observed that seismographs located at any distance within 105 degrees from the epicenter recorded the arrival of the both P and S wave. However, the seismographs located beyond 145 degrees from epicenter record the arrival of P waves, but not that of S wave, and thus a zone between 105 degree and 145 degree from the epicenter was identified as the shadow zone for both types of waves, and the entire zone beyond 105 degree does not receive S wave, and the shadow zone of S wave is much larger than that of P waves. Okay, now let us see again. So this is, as I told you, here. Okay, so this area is not receiving this P wave, and hence this zone is known as shadow zone of P wave. So here the area is between 105 degree and 145 degree. See here how it is measured. Let us say this is a vertical plane, and here this is a horizontal plane. Okay, and here this is 0 degree. Okay, here this is 0 degree, this is 0, and here this is 180 degree. And see here, okay, the angle found here is 105 degree. Okay, then another one here, the angle found here is 145 degree. So between 105 and 145 degrees we don't find any these P waves, and hence this zone is known as shadow zone of P waves. And likewise beyond 105 we don't find any S wave, and hence this zone is known as shadow zone of this S wave. And last of all, let us learn why the arcwave waves develop shadow zone. Can you tell me why do arcwave waves develop shadow zones? Why do arcwave waves develop shadow zones? Do you have any idea? Why do arcwave waves develop shadow zone? See here, see the diagram again. Here you are seeing banding. Okay, here you are seeing banding of the S wave. See here, it is banded. Here refraction is there. Why it is refracted? It is refracted depending on the density of the material. If the density is different from place to place, then the arcwave waves also banded. Refraction will be there. And here also these P waves also banded, because see, as we discussed earlier, here after the crust we have this mantle which is in partly molten state. Okay, and in the core area also we have the outer core is composed of liquid and the inner core is solid, and that is why even the P waves also banded. Okay, even the P waves also banded and refracted, and that is why here in this area shadow zones are developed. And here in this area also see these all the S waves which cannot pass through the liquid state, cannot pass this core area, and hence in this section shadow zones of S waves develop. because we know that the outer part of the core is composed mainly of these liquid materials, and these liquids, through these liquids the S wave cannot pass through, and that is why the traveling has stopped, and that is why a big shadow zone of S wave is developed, more than the 40% of the Earth surface. And this is why arc waves develop shadow zones. So you have to read this area very carefully. Okay, see this area. See here. Okay, this area and this area. Direction of the waves change as they reflect or refract when coming across materials with different densities. Okay, so even in physics also, okay, you have learned about this reflection and refraction. Okay, see when light, let us say this is body water, and when light passes through through the water, see it is banded like this, because density of the air and the density of water is different, and that is why the light, the rays are banded here. And in this way arc waves are also banded when they pass through the medium having different densities. Okay, so any question from your side? Any question? Do you hear me?
Yes, sir.
Okay, let us stop here for today. Attendance is very poor, but do not forget to send your names. Last time also some of you did not send your names. Okay, so please send your names in the WhatsApp group for attendance. Thank you very much for joining my class.